everyone. We are going to be looking at symmetry of projectile motion notes today, and this should be copied down in your lab notebook. So right at the top of your paper, symmetry of projectile notes. And today we're going to talk about symmetry and look at, in particular, an example of a soccer ball being kicked and eventually making it back to the ground. And we are going to label these different points. This should feel kind of familiar, like the Nerf gun lab. B and D are at the same height. C is at the peak, and then A and E are also at the same height. So we're given some information that the initial velocity of this soccer ball is 5 meters per second at 36.9 degrees. And that is all of the information that we get. So this right away, when I see a velocity given to me at an angle, that tells me I need to make a vector triangle, because that is not my x velocity, that's not my component in the y direction, that is my velocity. That is how fast I am moving at that direction. So I'm going to need to figure out what my components are. And when I look at this diagram, I see that my vector is going to be going up and to the right. And so my components need to be up and to the right as well. And then I know that this is theta, or that 36.9 degrees. So I'm going to break down my sine of theta and cosine of theta in terms of these velocity variables. So sine of theta is going to be my opposite over hypotenuse. So the opposite in this case is my initial velocity in the y direction. And then my hypotenuse is that initial velocity. And my cosine is adjacent, which is that v initial in the x direction, over the hypotenuse. And using both of these definitions, I'm going to be able to solve for these components, for that initial y and that initial x. And I'm actually going to do that right now, because I don't want to forget when I'm trying to solve my problem later that I need to split up that velocity into components. So my initial velocity in the y direction, that y component, is going to be that initial velocity times sine of theta. And so that's going to be that 5 times sine of 36.9. Make sure your calculator is in degrees for this class. I know maybe you have it in radians for your math class. But you should get about 3 meters per second. And then if we solve this one, we get VO times cosine theta will give us that x component. So 5 times the cosine of 36. .9. My stylus isn't working, sorry. That should be a 0.9. And that should be about 4 meters per second. So now I have my components which will come in handy later. And should both of those be positive numbers? Yes, because VOX is to the right, which is positive, and VOY is to up, which is positive. Okay, now we don't just want to solve for that initial point. We want to solve for B, C, D, and E. So we are going to make another chart, and our first column is going to be location. So we're going to have location A, B, C, D, and E. So again, you should be copying all this down in your lab notebook. Our next column is going to be the acceleration in the x direction. Next column, acceleration in the y direction. And this is not something that you should copy down necessarily every time that you're solving one of these problems, because you might not have to solve for everything every time. I'm actually going to give this velocity column a little bit more room. So let's talk about what Vy and velocity and speed mean distinctively. So Vy is the y component of the velocity at that location. Velocity is the velocity, so we already know one of these velocities. It was given to us. We know the velocity at A, which is going to be 5 meters per second at 36.9 degrees. We know that that's the velocity. Now, we know a lot of other things in this chart as well. We just solved for the velocity, y component, at A. We know that this is 3 meters per second. And there's some other information that we can infer based on our physics knowledge and rules of projectile motion. So I hope that you've already kind of thought about this, or maybe even already filled it in. But our acceleration in the x direction, so that horizontal motion in projectile motion, is always constant velocity. There's no acceleration in that horizontal direction. There is, however, acceleration in the y direction, and that acceleration is always down, and it is always the magnitude of negative 9.8. Because we are in free fall. Okay, now there is one extra piece of information I need to give you, and that is at B. So we have our x component, that y component of that velocity, and the y component is 2 meters per second. Is there anything else that we can fill out in this chart without really having to solve for anything? No kinematics equations. The velocity at the peak in the y direction, so the velocity at C in the y direction, is 0. If I were to draw in the velocity vector at C, I would expect to see something completely horizontal. Okay, Now, there's some principles of symmetry we need to discuss. So one is, and we've kind of talked about this, is that when you're at the same height, those y direction velocities are the same but opposite. And just kind of to prove that symmetry of the y velocity, it is only when they are at the same height. So let's compare going from B to C versus going from C to D. So there's some things that are the same: the acceleration in the y direction, the change in displacement, and while this isn't the same, the velocity at C is 0, and both of these motions share that point. So if we look from B to C, we want to relate the other velocities, so basically the two velocities, initial and final, the change in y and the acceleration. So the equation we want to look at is this one. So let's first look at B to C. From B to C, C, the velocity is 0, so that's the final. And we are left with that -1, that initial velocity squared. So that's like the velocity at B. I'm going to replace that actually with VB. We know that 2 is constant. We know that acceleration in the y direction is constant, and we know they travel the same displacement. So that must mean, when we look at this proportional reasoning, that that velocity is going to be the same. So that is why that velocity is the same. All of these things are the same, it's just that we flip those initial and finals. So that means this is going to be -2 meters per second. And at E, we'll be traveling at -3 meters per second in the y direction. So to get these velocities, you have to kind of do the reverse of how we found those components at the beginning. So when we drew our vector triangle, we found the components. Instead, what we have here is we actually have the components. We know that that x direction velocity doesn't change. We know the y direction is 2, and the x component is still 4, and so it's our job to find theta and v. So v can be found using that Pythagorean theorem of a squared plus b squared plus is equal to c squared. So if we do 2 squared plus 4 squared, and then take the square root of that, we get about 4.47, but we are not done yet because we need to find theta. And theta can be found by using the tangent. So tangent of theta is opposite over adjacent. So in this case, that would be 2 over 4. So we'll have to do the inverse tangent of 0.5 to get theta, which ends up being about 26.5 degrees. And it should be a positive angle because it is above the horizontal. Now this one, if I draw in my vector, I should just have that horizontal component. So that means it's just that 4 meters per second. And the angle is at 0 degrees. There is no angle above the horizontal. Now this one, we have -2 and 4, and we want to find that angle. So from the horizontal. So basically from the x component is where we want to find the angle. And if you notice, that theta will be tan of theta will be opposite. So that's 2 over 4, -2 over 4, which is -0.5, which will give us theta. And that actually ends up being, and maybe you know this property, but it is the negative angle of positive inverse of tangent of positive 0.5. And same sides of the triangle, we are still going to have a 4.47 meters per second. So there's not only symmetry in this y direction, but there's also symmetry when we compare those resultant velocities and what direction they are traveling in. So then when we think about the speed is just how fast you're going. Speed is the scalar version of the velocity vector, and so our speed is just 5, is just 4.47, and you'll notice the pattern. So the reason we learn this is because you can solve for very few things from these problems, but you can figure out a lot more because of the principles of symmetry. So this one just means that it's below the horizontal. And that is all the notes.